Okay. Now it's turned down. All right, so wrapping it around, you need the outside and inside radius, right? So the outside radius is distance from here to here. The inside is here to here. So the outside is going to be the distance from the x-axis to here, which is just the function, which is what? 2 over x. That's this one. But you have to add this distance, which is 2. So that should be 2 plus 2 over x. That's the outer one. The inner one is the bottom function from the x-axis to here is what? From here to here? That's the x minus 1 squared. But then you have to add 2. So you can write it different ways. X minus 1 squared plus 2, or you can put the 2 in front. That's your inner. And then you have to just go to the formula. And since you're using, what, washers, shells? What is this? Washers, right? Washers. Shells is the problem on the back. So you'll have pi integral 1 to 2. And then you'll have outer squared minus inner squared dx. So just take this right here, 2 plus 2 over x, square it, and then that, and that's all I wanted. That's it. Just plugged in. 2 plus 2 over x, and then x minus 1 squared plus 2. All right? Let me see where I am here. All right. The one on the back, did anyone do the one on the back? Tried it? Okay. The one on the back, I'm going to go really, really fast. You got that same region like this, same rectangle. You're rotating around this. So the integral is 2 pi, integral 1 to 2. And then you just got to know the radius, which is the distance from the axis of rotation to your rectangle. So the distance from here to here, I believe, was 3. Yeah, that was 3. And the distance from here to here is x. So here to here, which is your radius, is 3 minus x. And then it's the top function minus the bottom function dx. You're done. So top one is 2 plus, sorry, not 2 plus. It's just 2 over x goes here minus the x minus 1 squared goes there. All right, and dx. So that's what you should expect on your exam, okay, where I give you a region. Now, most likely, I will give you at least one where I give you the region, the picture like I did, and then ask you for a couple of rotations. Usually, I'll ask you for x-axis, y-axis, x equals a number, y equals a number. 4 rotations in one problem, and I'll probably ask you 2 or 3 problems. So the speed at which you get those formulas set up is important. That's why I wanted to give you this quiz, to give you an idea of what I would expect you could do in 8 minutes. I think this is maybe, I don't know, 12 would be tops that you should need for this. So I think we're not there as a class yet if we're not all getting this within that time frame. So you're going to have to work on the speed of things, all right? All right, well, it's just one quiz. Don't worry, I'm going to drop at least one. If we have 12, I'll drop 2. I think this was the 6th one. So I'll try and do weekly quizzes. They just eat up too much time. 15 minutes gone. All right, so this is what I want to start with today. And I'm facing this way because there's some stuff I want to show you that my internet students are going to need to see also. So see how this works, all right? I have no idea how the video quality is going to turn out here. Especially when I turn the projector on. I don't know if I'm going to get glare, if the brightness is going to wash the video out. I'm not sure. All right, we finished up last time. We were doing arc length, right? And I proved at the end of class that the circumference of a circle, right? I proved that, and there was a few of you that liked it. Nobody else did. So now what we're going to do is change our perspective. We're going to look at the same idea of taking a function. We're still going to wrap it around the x-axis, all right? So we're not going to take it off and measure how long it is. We're going to wrap it back around the x-axis like the good old days. But instead of looking at the volume of this, we want to know the surface area, right? That's what we want to know. And last class, we said that if we had a curve, we can measure its length by the integral a to b. Anyone remember? It's kind of ugly. Y prime squared dx. Remember that? And I showed you we had to pick the problems very special or else it wouldn't work out. Well, this problem, as we're about to see, the integral that we're going to get from this to get us that surface area is actually connected to this. And you'll see why. What have I done? What have I tried to instill in this class? Every time I've tried to set up a formula, I've always tried to back it up with geometry, right? I've always tried to show you a picture of where the formula comes from rather than just giving you the formula. So I'm going to do the same thing here. Imagine that we're going to take a little band off of this surface, right? If we could figure out what the area of that band was, then we could add them all up, right? And get the total surface area. So let me try and figure out where I could find the area of that red band from, all right? So where could I get that? Well, what I could do is I could almost imagine, again, taking a rectangle like this, right? And wrapping it around. But I'm only concerned about this top edge, right? That top edge is going to create the surface. Do you agree? The top edge of this creates the surface. The stuff on the inside would have created that inside piece. That would be the volume, and we already did that, right? I just want this outside edge. Are y'all with me? Y'all look stunned from that quiz. Are y'all all right? Okay, so let me take this red piece and just show it to you over here. The difference between this one and what I've drawn before is that this is more like a rubber band in the sense that it's just a real thin edge, right? Put my hand through there. So what is the area of that, right? What is the area of that? So I get out my scissors and I cut it, right? And I lay it open. And if I lay that open and turn it sideways, I get this big, long piece of tape, basically, right? And we know the area of a rectangle, don't we? It's just length times, in this case, the height. Yeah? So it seems like that's all I have to do is figure out how wide this is, figure out how long that is, and I'm done, right? But there's a little bit of a subtlety in here. I don't want to use a flat rectangle. I do not want to use just a straight edge across here. And the reason why is because this is a curve, right? It curves a little bit. What would be even better is if I were able to account for that little waviness here, right? That little waviness in there that I might get. And so this edge over here has the waviness of the curve in it, would be this edge, wouldn't it? Like that. And what is that right here? It's always been dx, hasn't it? It's always been dx because we've assumed it's just the width of that rectangle. But now I wanted to account for the curvature. It's the length of that piece, isn't it? It would be a better approximation if I used the length of the function right in there, wouldn't it? That's the way I'm going to do it. Instead of using just a solid straight line, I'm going to use the length of the curve right there. And, well, last class, we learned that the length of the curve is this, isn't it? So this piece right here is going to be the height of a rectangle. And then this piece is what? It's the circumference of this, right? Take this, imagine from here to here. If I cut that open and laid it out, it would be the circumference. We've done that before. The circumference is 2 pi r, isn't it? 2 pi r. So this should be 2 pi times the radius. But what's the radius? What is the distance from here to here? That's the height of the function, isn't it? That's how tall the function is there, which is f of x. I can call it f of x or I can call it y, can't I? Let's call it y. That is the area of that one red band going around the function. Then what I'll do is I'll move this thing back and forth, right? And I'll add them all up. And that gives me the surface area. So my formula then for surface area should be what? I'll leave the length formula up there. Should be what? This times this, right? Oh, sorry. This was dx. It's the formula for it, the entire thing. This. So it should be integral, right? What goes out front? 2 pi, because I have a constant right here. Also, let's call this SA for surface area. You could do S dot A dot. Surface area will be 2 pi and then y, right? Which is f of x, same thing as f of x. Square root of 1 plus y prime squared dx. That is the formula for the area of the surface generated by wrapping a function around the x-axis. Now we also need the limits of integration, right? A to b. A to b. A to b. I could replace in here, right? Y's could all be replaced with f of x's. This could be f prime of x, and it would be the same formula, wouldn't it? Okay, just keep that in mind. All right, that's it. Now, I'm not going to give you a lot of problems off of this. It's just more to expose you to it. Yes?
Just for clarification, your y came from your r?
Yes, my y is the radius.
Okay.
It's the function's height right here. This was f of x, which is the same as y, right?
Okay.
Why is there a dx at the end and not a dy?
You have to go back from last class and figure out where we got this from. This we got from doing a arc length and approximating it with the right triangle, calling this dx and calling this dy, and then using Pythagorean. And then we factored something out of the square root, and what popped out of the square root was the dx.
So are we going to replace anything?
Are you going to
Replace the y?
with f of x? So like if, well, let me do an example, okay? So how about this? I had in mind today what I wanted to find the length of, the surface area of. I thought that you might like it. What do you think I was going to find the surface area of? A sphere. Exactly. Y'all interested in that? Okay. Would you like to find the surface area of a particular sphere, like with a certain radius, or do you want me to do a general sphere where we actually create the formula? You want the formula? All right, so you want me to create the formula? Okay, let's first look in the back of the book. What's the formula for the surface of a sphere? Someone gives you a sphere. What's the surface area according to the formula? Four pi r squared. Right? I beat you to it. So 4 pi r squared is the formula for the surface area of a sphere that has a radius of r, right? So how could I come up with that formula? Take a fourth of a circle, right, and wrap it around the x-axis? So take a circle of radius, what? Little r, right? R this way, r that way. A circle with radius little r, wrap it around the x-axis, and then double that answer, and it better be 4 pi r squared. Yes?
Is it just a coincidence that that's the derivative of volume of the sphere?
In some respects, yes. Yes, coincidence. Yeah, I'm trying to think of like beyond this if there's something like way out there that I've looked at before, but right now I don't believe it's connected. Like you can't arbitrarily take the volume of a solid, take its derivative and get the surface area. So it's more coincidental than anything else. Okay, so you ready? What do we need in order to do this then? What do we always need to get if we're going to, the equation, the function itself, right? I think we've done this enough. I hope we have. That this would be f of x is equal to the square root of r squared minus x squared. Remembering that r in the problem is a constant, right? The variable is x. So what are the things we're going to need for the surface area formula? We're going to need the derivative, right? And we're going to need to square it and add 1 and do all that junk that we did before. So I like to do all that on the side first. I like to actually figure out what's the derivative of f. Well, we did that last class too, didn't we? Or class before? I think it comes out to be negative x over square root r squared minus x squared. That's your derivative. Do y'all agree? Okay, and then we have to do what with that in the formula? Square it first, then add 1, right? So I need to square this. Notice I'm using f prime instead of y prime, right? So when we square it, we get this, right? And now I'm going to go and set up the formula. So the surface area should be 2 pi integral what to what? 0 to r. And then y, right, which is f of x, which is square root of r squared minus x squared, times the square root of 1 plus the derivative here, right, the derivative squared, which is this. That's it. That makes sense? That does not look like a fun integral, does it? Not yet. What did we do last time? We got a common denominator. We put these together. So what would we get if we put those together? I'm going to erase this. Two pi integral 0 to r square root r squared minus x squared times square root of, what do we get if we put these together? I put the 1, this together. R squared over r squared minus x squared, right? Dx. Yeah? That's exactly what we did last class at the very end. The only difference between what we're doing now and last class is this piece and 2 pi. That's the only difference, right? Now, last time what happened is that I took the square root of each one. The square root of r squared was r, and I popped it out. And what we had left was 1 over that root, didn't we? And then we actually used a formula right out of our book. We said we could have used trig sub. This time, it's even going to be better. Because, do y'all see what happens? If I do this, I take the square root of top and bottom, right? Separately. These two cancel completely. And all you're left with is what? Square root of r squared, which is just r. And can I pull that out of the integral? An r out? Yes, it's a constant. So I have 2 pi r integral 0 to r of what? 1 dx, right? Just 1 dx. What's the antiderivative of 1 with respect to x? X. So this is just 2 pi r x evaluated 0 to r. Right? Antiderivative of 1 is x. Now plug in r, what do you get? 2 pi r squared. Plug in 0, what do you get? 0. So this is our answer? but that was half of the sphere. So double that answer, and what do you get? 4 pi r squared. So that actually turns out to be an easier integral. I don't need any formulas at all. The main part of this demonstration is just really to show you that the only difference between surface area formula and arc length formula is the 2 pi out front and this additional f of x that'll be here. Sometimes that f of x will make this nicer. Sometimes the f of x out there will make it more complicated. So I want you in your book, why don't you try for homework. I didn't give anything off of this last time, right? Okay, so how about page 397? Maybe something like 5. That's very, very basic. Number 7. Number 11. Oh, whoa, whoa, whoa. Scratch 11. Scratch 11. Maybe 10. 5, 7, 10. That's good. That's it. Done with that section. All right? Just wanted to show you how it worked, right? We're not. I told you last class, I'm not really getting real deep into the arc length and surface area. Just want you to see it, all right? See it once. Now, there is another section in the book that I'm not going to cover at all, but I want to mention something from it. It's 7.6, which, if I have enough time in a class, I will cover 7.6. But in my history of teaching this class, anytime I try and get into 7.6, I always have to give up something at the end, and I'm not willing to give up the stuff at the end for this. This section is called applications. So I know for a lot of you, like, I wish, I want to see this working in the real world type thing, and I understand that completely, but that's the difference between a math class and an engineering class. And in the engineering class, that's where you can do the application. What you need to know how to do is do integration and do that. So hopefully you've got those tools. But let me just mention a couple of things that you can do with applications that this section talks about. One of them is, if you have from physics that work equals force times displacement, and later on that becomes a dot product, and it gets more complicated than just traditional multiplication. But work is the force applied on an object times the displacement. So if I drag a body across the room, it's Halloween, okay? So I'm dragging a body across the room, right? And so I'm applying a force on it over some distance. Then I multiply those two and I get the work that I've done in moving the body across the room, right? So if you have force here and displacement here, or the other way around, then the area underneath this comes from a bunch of these rectangles, right, that I put together here. And each one of them, the width is a force and the height is a displacement. And so the area of that is a force times a displacement. So that little sliver, the area of it, represents the work I did on that little infinitesimal slice. And so if I add up all the area, I get the total work done. I talked about this in the very beginning also, so maybe now it makes a little more sense. But these two variables, whatever they are, whatever they multiply to be, if that quantity has meaning, like in this sense it does, then the area is going to be something useful to us. Another application that's kind of interesting, I didn't bring, I can steal this. Let me see. Someone's going to get mad at me for this. All right. Nobody saw me do that.
It's on camera.
No, I was off camera.
Right.
This is the way I found it. So this is what we would consider to be, we call this a lamina. It's a sheet of paper, basically. All right? we call it a homogeneous lamina, meaning that we are assuming that whatever this is made out of, it's uniform throughout the entire surface. Now we know that's not true because, the way I tore it, it's actually thinner over here than it is over here because I tore some of the inside out. Y'all see that? But let's assume that it was the same throughout. Then we call this a homogeneous lamina. And so if someone gives you a homogeneous lamina like this, we actually can use integration to find its center of mass, to figure out the point, wherever the point is, that represents the center of that mass. And what's the center of mass? It's basically the point that you could balance this. I think I tore it out, right? I think I did. I'll change it a little bit. I don't know. I don't think I'm going to be able to get this. I might have to cheat. There we go. Okay, so there's your center of mass. So the entire object balances on that center of mass point. And so with integration, we can find the center of mass. There's formula for it. You can look it up in the book, all right? It's just a simple, well, not as simple. It's just an integral, though. That's all it is, all right? Not only that, if later on in calculus, if this is a non-homogeneous lamina, meaning it does have variation in density throughout the object, you can still find the center of mass. But you have to account for that. So the integral becomes more complicated. And you'll do that like in Cal 3. You can do applications that way. So that's kind of cool. And especially like if the center of mass falls outside the object. Is it possible for the center of mass, something center of mass to be outside the object? Absolutely. Boomerang, right? A boomerang is an example of something where its center of mass is not on the object itself. A sphere, right? Take a sphere. Imagine it's a hollow ball. Where's the center of mass? It's in the inside, right? It's not on the surface. So centers of mass never have to be within the object itself. So, but we can find those centers of mass using integration. We can also find what are called moments of inertia. And that has to do with an object's resistance to rotation. So if I give you, let's see, this is kind of, what would be easier for me to do? Oh, shit. Would it be easier for me to spin this like this? I'm talking like how much force would it take for me to spin it like this versus if I turn it this way and try and spin it like this? Which one is going to require more force? What do you think? Are they the same? It depends on the object itself. It seems like the shorter one because your mass is closer to your axis of rotation, and the closer it is, the easier it is to turn. And so we can find that a number that represents that resistance to motion. That's what inertia is. Inertia is an object's tendency to want to stay in place, either moving, keep moving, or not. I remember my grandma was old school. She didn't want to wear a seatbelt. And I can remember my brother very distinctly. He told my grandma, put on your seatbelt. She's like, I don't believe in seatbelts. My brother said, you believe in inertia? And anyways, she didn't put on her seatbelt. But inertia, an object's going to want to stay in motion, right? So that rotation, right, is something we can compute using integrals. One more thing. Hydrostatic pressure. So you have a dam, right? You have a dam that's holding back water. If you want to calculate the pressure being applied at different points or the total pressure on the dam wall, you can do that using integration. And it's kind of a simple idea. It's hard to do generally. If this is a dam and you've got your water here like this, then what you do is you take like an infinitesimal layer like this and you try and compute like the force on at that infinitesimal layer, and then you add up all the infinitesimal layers. Something like that. All right. It all ties into cutting things up into little pieces and adding them up. Anything that requires that is where the integral is going to come in. All right. We good? Y'all ready to get out of chapter 7? Not really? You don't want to stay there, huh? I've been warning you about chapter 8. All right. We're still good. So here we go, chapter 8. There is a section, another section that we don't cover, 7.7, called Differential Equations. The reason we don't cover it is because you can take an entire semester course on differential equations. There's nothing I can say in 2 days that's going to give you any sort of good treatment of that topic, so we don't really cover it. Chapter 8, series. All right, we're going to start with 8.1, which are called sequences. There's a lot of definitions. There's a lot of theorems in this chapter. All right, yes?
This is going to be in third exam, right?
I don't know. We need to talk about third exam because I initially put third exam on the 12th of November so that anybody that thought they might want to drop the class could drop on the 13th. But if we have it on the 12th, man, your final is going to be loaded very heavy with chapter 8 because I don't think I'm going to get to maybe the third section at the most by the 12th, which means a lot of chapter 8 is going to be in the final. So I don't know. What do y'all think? Do y'all want to keep it at the 12th, or you want me to just kind of let it be flexible? You want to see some of this first and then tell me later?
Yeah.
Okay, all right, let's do that. I don't want to box you in, you know, I don't want you to paint yourself into a corner here. All right, sequences. So if we could, let me talk about what series are some of the applications before we even get started. That way you kind of have like a picture of why and where we're going. All right, so why do we do series? Series are used for a lot of things. Here are just a few examples. Signal processing. Signal processing. That has to do with, you know, you're running an experiment in a lab setting and you're collecting data, and that data you're trying to analyze. So signal processing is where series come into play. Differential equations. I'm just going to put diff EQ. Differential equations is the section I'm skipping in the book, or I'm not skipping, we're not covering because it's an entire semester course. To solve differential equations, you can use series. In computer science, CS, doing what's called numerical analysis. Anytime you have some sort of heat equations, which ties into the differential equations, but heat equations where you're trying to figure out heat transfer from one object to another, series come into play. All right, there's so many things that series are used for. I can't treat it properly. You know, I can't sit here and tell you every example. So if we could, can we get the projector on and the lights, all lights off? And please don't go to sleep. We're going to watch a movie. I brought in Frozen. I hope everyone's okay with that. Whoa. Here it comes. Here we go. I think I can see that. All right, so we've all seen the sine curve, haven't we? We've all seen the sine curve. So when you go and you get on your calculator, well, you shouldn't need a calculator for this. If I say, what is sine of pi over 4, everyone's like, sine of pi over 4 is root 2 over 2, right? Because that's one of the common angles. But if I say what's sine of just 4, then everyone breaks their calculator out, right? So what is your calculator actually doing to figure out what sine of 4 is? Is it sitting there going, well, I've got the sine curve, and I'm going to go out to 4, and I'm going to plug it in and figure out what it, I mean, what the hell is your calculator doing? All it knows really is what? I mean, what can a computer do? At the end of the day, what can it do? What's the only thing computer knows? 1 and 0, right? On or off. There's either an electrical signal there or not there. That's a 1 or a 0. It's binary. That's it. That's all it can do. From that, you can get a computer to do basic operations: addition, subtraction, multiplication, division. Right? That's it. I mean, there's nothing more. There's nothing more to it. So when you type in sine of 4, what is the calculator doing to get an answer? Or if you type in sine of pi over 4, if you don't know your unit circle, and it spits out root 2 over 2, it'll usually spit out the decimal, right? So where's this coming from? So this is where series come into play. What I want you to see here is right now I have a red function graph. That's the traditional sine curve, right? Yes? And then I have a black curve graphed right now. You can't really see it because it's the x-axis. It's the function f of x equals 0. I have it right there. You see it? 0? F of x is 0 is this black line. Do you think that my function f of x equals 0 is a good approximation of a sine curve? No. That's a terrible approximation. You wouldn't say that those two are close to each other at all, would you? Not at all. So let me tweak it a little bit. Let me change it to, instead of 0, how about x? Is that better? It's a little bit better. I mean, for at least at 0, it's the same, right? Yay, right? Sine of 0, 0. If I plug 0 in there, I get 0. So at least at one point, I'm close, right? I'm exactly the right. And then it's kind of linear. All right, so let me change it a little more. Let me make it, instead of x, how about x minus x cubed over 6? So now it's a cubic polynomial. Is that a good approximation? Well, kind of, right? Kind of. It's looking kind of good in here. Out here, I start to fall apart a little bit, don't I? So how about I add some more to this? Make my function more complicated. How about that? It's a 5th degree polynomial. You see this? How's that? It got a little better in here, didn't it? Now I'm going to keep doing this. Uh-oh. What did you? Okay. Do you see them? Do you see them? Now I'm leaving the dotted ones. Those are the ones I'm leaving behind, okay? So you can see that the black curve is actually getting better and better, isn't it? Now I'm actually at a 17th degree polynomial, right? I have a 17th degree term in there. I've got a 15th degree, a 13th, an 11th, a 9th, a 7th, a 5th, a 3rd, and a 1st degree, right? Notice there's no evens in there. No even powers of x. They're all odds. If I were to continue this and continue building this, what would happen is I would actually be able to get a black function that gets closer and closer to being on top of the red function. And if I go forever following a certain pattern, because there is a pattern in this, the powers keep coming up by 2, right? These numbers, though, where are those coming from? Well, there's a formula for it. We'll see it comes from what's called Taylor's formula. And this is what we call later on a Taylor series. It's later on in the chapter. And so what we can do is we can take a function and we can model it with this Taylor series, and we can make our Taylor series as close as we ever want to be to the true function. And that's what your calculator is using to figure out what sine of 4 is. See, if you plug 4 into your calculator, what your calculator does is takes this polynomial and plugs 4 in. Why? Because your calculator can very easily do 4 cubed, right? 4 times 4 times 4. That it can do. It can do 4 to the 5th power very easily. 4 to the 7th, because the computer is fast, right? It can do arithmetic much faster than we can. And so what happens is these calculators have built-in algorithms where they go out. They don't go out. I mean, if we could go forever, it would be the red function, basically. We can't go forever. So the calculator stops at some preset, predetermined tolerance and spits out an answer. That's what it's using, though. It has no idea that sine is this wavy-looking thing. Has no clue. It looks at it as a power series. All right? And this goes for just about any function you can think of. Here's the function 1 over 1 minus x, the red one. Is my approximation good? 0? No? Okay. Is that better? 1 plus x? Better. 1 plus x squared, that okay? Do you see what's happening? Now notice that between about here and here, my black function is getting better and better, isn't it? But outside, this way, it's not doing good, is it? Okay, this is what we have in this case is we have a series of power functions. Notice my language there? A series of power functions, which is pretty darn close to the function I'm trying to approximate within some interval. And we call this interval where it's actually doing a good job, we call it the interval of convergence. And we will have to later on find out what that interval is. All right, we'll have to actually determine, like in this case, it would be from -1 to 1. And then if you want to figure out what's going out here, we will have a way of shifting our approximation over using what's called the Taylor series, and we just shift it about. So, yeah, huh? What's different between this series of power functions and the one before? It has evens and odds, doesn't it? Has evens and odds. Let's look at another one. E to the x, the exponential function. 1 plus x, 1 plus x squared over 2. Look at this one. Can you all see that? Look at that. It looks like even if it doesn't look like I'm going to run into that same problem I had on the last one. You know, on the last one, there was this point at which my approximation just sucked after that. It looks like the further I go out, I still keep on getting closer to the red function. So it turns out that for e to the x, this power series is always going to converge. So the interval of convergence actually is the entire number line. And so you could actually define e to the x to be this function. And that's what your calculator thinks it is. All right. This one, e to the negative x squared, looks like the red one. If I come up with the power series here, see, it's working, isn't it? I'm able to approximate it. I can keep going out forever. Looks like it's going to work. It's this right here. Now, why is that important? Because if I were to ask you right now to integrate e to the negative x squared, I mean, if I were to say, all right, everyone, quiz, what's the integral of e to the negative x squared dx? If I were to ask you to do that right now, nobody in this class would be able to do that. Nobody. And remember, there were two fathers of calculus. I don't know if y'all heard this back in Cal 1. The two fathers of calculus were who? Do y'all know? Newton and Leibniz. Isaac Newton and Leibniz. I don't know Leibniz's first name. Both created calculus independently of each other on different parts of the world. And then found out later they were doing the same thing. So if I ask you to integrate this, you wouldn't know how to do it, but guess what? Leibniz wouldn't know how to do it either. Newton would. Because Newton had power series. He had actually come up and was onto this. So watch, if I want to integrate e to the negative x squared, right? If I want to do it, if I can rewrite e to the negative x squared as its power series, could you integrate 1? Antiderivative of 1? Yes. Can you integrate that? That? Yes? And so in order to integrate e to the negative x squared, even though there's no technique of integration to do it, if you first rewrite e to the negative x squared as its power series, you could integrate term by term, and you could get an answer as close to the true answer as you ever want it to be. So it's much more powerful with this series idea. I'm trying to sell you on the value of this. I don't know if I'm working here. How about here's sine of x cubed? See, even something like sine of x cubed, I can approximate it. What do you notice about the sine? The approximation of the sine, they're all what? 3, 9, 15, 21? they're all divisible by 3, but even less than that, they're all odd, right? And what about that cosine one? They were all what? Even. Hey, wasn't cosine an even function? I wonder if the word even has anything to do with that. It's exactly what it has to do with. That's where it comes from. The idea of an even function is that its power series involves even powers. An odd function, the power series involves odd powers. And if you mix them up, then it's neither even nor odd. So you didn't probably know that, but now you do. It's actually tied to this whole thing, power series. All right. One more thing. At some point, I'll probably offer this as like a bonus Fourier series. It's not in our book, but this is something that computer scientists deal with. Ruben, come on. Maybe like a lecture you can come into, like I'll offer you come in for an hour and we'll meet in a room and I'll go through this whole thing just to expose you to a Fourier series, but I can't take any time in class for it. This is what I want to show you. Remember I was talking about signal processing? So like you have this data where you're getting either signal or no signal, signal, no signal, something like that, and you have all this data and you want to somehow analyze it. You want to treat this as a function. But the problem with something like this is that we don't have functions that behave this way. This is like piecewise functions, isn't it? This is like a piecewise function. So I wonder if there's a way that we could approximate this with a nice continuous function. And that's what a Fourier series is. So I want you to see the Fourier series come in. Is that a good approximation of that? It's okay. Is that better? See, what this is it started out as a sine curve, but it's actually a sine curve combined with other sine curves and cosine curves that creates almost this drop-off table, like a table drop and then back up, this stepwise function. But it's continuous, because if you were to draw it, you'd be squiggling, like vibrating almost, right? And then you would go up and down, then you vibrate. And so it's a nice continuous differentiable function as opposed to the original one, which had a bunch of breaks in it. So we can use that blue curve to approximate this, right? And so if you have something like someone singing and you're recording it, it's basically a bunch of waves. And if you can somehow model those waves with this, it's easier to compress that data. You get smaller file sizes and things like that. The compression of it's much nicer. So they use Fourier series for things like that, audio compression and blah, 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 blah. All right. Lights. I put too many people to sleep there. And can you turn the projector off? Thank you. That was just to try and sell you. I don't know if that worked. But. All right, here we go. So 8.1, sequences. Let me zoom this back in. Did I hear someone go, oof, oof, oof? Is that music I heard out there today? Did y'all hear that? My gosh. It was too loud. I went up to them and told them to turn it down. I was all the way over here and I could hear it. Was anyone in the science building when it was on?
Yeah.
Could you hear it?
Yes.
It's ridiculous. All right, I have 40 minutes. Let's see what I can do in 40 minutes. Sequences. So before we talk about series, we must first understand what a sequence is. Then, once we understand sequences, we can get into the series. So when you see the word sequence, what do you think of? Yeah. Sequence.
That's as good as mine gets.
Okay. All right.
That's all I got.
This is a list of ordered numbers. Now, in general, for those of you who might be going on to study math, like more of a pure math or computer science, a sequence does not have to be a sequence of numbers. You can have a sequence of functions or a sequence of whatever. All right? But in this class, for this chapter, we're going to look at it as a sequence of numbers for now. But it's ordered. So there's a pattern to it, or there's a first number followed by a second. If you switch those orders, it's no longer the same sequence. It's something different. So we like to write this list as follows. A set of braces to let you know that we have a list. It's A1, A2, A3. And then this list might stop somewhere, in which case I would call this A sub k. And this list would have k numbers, right, in it. And so we call this a finite sequence. Finite, stops. As opposed to another type of sequence where we could have a list of numbers, A1, A2, A3. And then if I don't want it to ever stop, I usually use 3 dots. 1, 2, 3. That's the standard in mathematics, to use 3 dots to represent, continue that pattern forever. But if you ever see me just go dot, 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 like, you know, we all understand what I mean, right? I've never been real tied to the 3 dot thing. Sometimes it's 4, sometimes it's 8. It just depends on how much I want to emphasize it keeps going, all right? So this is going to be an infinite sequence. This was a finite sequence. Okay? Pretty standard, pretty basic, yes? No craziness yet? All right. Now, there's another way that I want you to view a sequence, and that's as a function. A sequence is also a function. Now, let me elaborate on this a little bit. We're all familiar with something like this, f of x equals x squared. That's a function, right? If I ask you to graph it, you would draw me a little parabola like that, wouldn't you? And the reason why you draw a parabola is because we have to have a way of representing every ordered pair, right? Like when I plug in 1, what does it spit out? 1. When I plug in 2, it spits out 4. When I plug in 3, it spits out 9. But there's all the other stuff too, right? When I plug in 1/2, spits something out. Everything in between. So that's what this curve is about. It's about trying to fill in the entire picture, isn't it? Yeah? Okay, so when we look at a function like this, we've kind of subconsciously agreed that x is a real number. X is an element of the real numbers. So that the x that you plug in here can come from anywhere in the real numbers, anywhere off that number line. Yeah? What if I now take that function and I restrict it? And instead of taking the function and saying it's a function of x, I say it's a function of n. And I define it to be n squared. And I tell you that n doesn't come from the real numbers. It comes from double-struck capital N. Now, what does double-struck capital N mean? You've probably never seen that before. Maybe you have. Anyone know? It's the natural numbers. This is the real numbers, the natural numbers. So what are the natural numbers? The natural numbers are the ones that you would think naturally occurred first, and that's 1, 2, 3, all the way forever. Those are the natural numbers. It's the set of all the counting numbers, 1, 2, 3, 4, 5. Yes? Not 0. 0 came later. 0 was a big deal when they figured it out. Like, oh yeah, we might need to use 0. If you believe in the history of progress of the way that thought happened, you know, it was a lot of trading of things that our number system was needed for. So I don't walk up and be like, I'd like to trade 0 goats. Zero just wasn't necessary until later. So 0 came afterwards. So those are our natural numbers. All right, so what if I restrict you there? Can you graph this? You're going to only be able to plug these numbers in, right? Which means that when you plug in 1, you get what? 1. And when you plug in 2, you get 4. And plug in 3, you get 9. And so, do I connect them? I don't, because that's all I'm allowed to plug in. So instead of it being a nice, smooth, continuous function, this is actually a function, but it's a bunch of dots as opposed to a nice, smooth curve. Do you see that? And it starts at 1 and goes forever, and there's just a bunch of dots going up. Now, do you agree that all those dots do lie on this parabola? It's just all the pieces in between aren't there. Yeah? And that's what a sequence is. See, we get away from this notation, and instead of writing down this, we say, no, because that's too confusing, you're going to think it's this. We write this instead. A sub n equals n squared. This is the notation that we use to define a sequence. I say, it's kind of like saying f of n. This is almost like saying f of n. But with the subscript notation, I'm telling you this is a sequence, and I'm telling you, by writing it this way, that the n is going to be from the natural numbers. Unless someone else tells you otherwise, you are to assume that n is always going to start at 1. Unless we say otherwise, which we will, but not yet. All right? So can you see that a sequence is a function? It just goes from the natural numbers into the real numbers instead of the real numbers into the real numbers. Yeah? All right, some alternate notations. We're just trying to get a bunch of preliminary stuff out of the way here, all right? If someone writes down a sub n equals n squared, I'm giving you, that's just one example. Another way they could write it is this. Okay, so this is one notation. This is another notation. They could even do something like this. What would that mean, do you think? Started at 3 instead of starting it at 1. So let me write next to this. What is this sequence? Tell me what this sequence is. What would I plug in first? 3. What's 3 squared? 9. What's next? 16, 25, so on forever, right? That's what that would be. As opposed to this, which